Os voy a presentar a Ilfak Guilfanov. Él, muchos lo conoceréis, es el fundador de Hexrace, el creador de IDA Pro. Hace mucho tiempo, cuando empezábamos a hacer los primeros Rooted Labs, José Ancoret iba a dar un Rooted Lab de reversing con IDA Pro y otras herramientas, y se me ocurrió la idea loca de mandarle un correo a Ilfak. Me puse a rastrear la web hasta que encontré su dirección de correo, le mandé un correo y le dije: nos vendría muy bien que nos prestaras licencias de IDA y tal. Y yo pensé que iba a ser un correo de estos que iban a ir a null. Me contestó Ilfak a los 2 minutos diciendo: no te preocupes, las personalizamos y además os ponemos el logo de Rooted dentro de la licencia. Yo aluciné, claro, digo, joder, este tío me ha contestado en 2 minutos y además en positivo. So thank you so much, Ilfak, because I do remember everyone who helped me in every project, and whenever we need licenses from IDA Pro, you were there for us, so thank you so much. He has a high skill profile in reversing and every discipline in security, so it's not good in colors, sorry, Ilfak. So it's your public and all yours, okay? I will give you enough time, don't worry about the time, okay?
Is something? Okay, it's a color problem. Good morning, everyone. Buenos dias. I don't speak Spanish, sorry, so I will give my presentation in English. There are so many people. Anyway, I will talk about the Decompiler internals. This is a presentation outline. First, I will talk about the Decompiler architecture and other things, the microcode and how it evolved and why we use it and so on and so on. If you want, you can follow the presentation online. The slides are available on the website. You see the URL on the slide. I hope that you have heard about our decompiler. It's called Hexrace Decompiler. It can work with binary native code. It's interactive, very robust, and programmable decompiler. We have it since 10 years now. It runs on top of IDA Pro, and it can handle not many processors for the moment. We support only x86, 64, and ARM, both Bitnesses and PowerPC. We could add more processors, but so far we feel that it's already good. That's why we don't go further. But maybe in the future we'll add MIPS as well. There's not a problem, but there's something shortcoming of this decompiler. While it was programmable, we did not open its internals, so you could not really go inside the decompilation engine and play with it and use it for your data analysis tasks. And now, since 2 days, it is possible. And this talk is about the internals of Decompiler, and we will talk about this intermediate language. If you talk about the Decompiler, Decompiler has several steps. First, we generate some intermediate language we call microcode in our decompiler. Then we transform it and kind of optimize it and make it smaller, shorter, and clearer to read. Then there are other steps like allocating local variables, generating the C tree, and beautifying it. And finally, we print it to so the user can play with it and study it. In this talk, we will talk only about the first 2 steps, how we generate the microcode and how we transform it. Unfortunately, I don't have enough time to tell you everything about the microcode. It's a huge thing, but at least I will introduce the microcode so you know how to work with it and how it works. One of the questions you may ask, why do we need the microcode? There are already many, okay. Why do we need the microcode? First of all, microcode is a very good thing because it lets us to get rid of all processor-specific stuff. Like every processor has its own special things. Like take, for example, x86. You have segment registers, the floating point stack. ARM has some mode addresses. When the lowest bit means that we have some mode, otherwise we have ARM mode. PowerPC has multiple copies of the carry flag, which is kind of unusual. Usually we have only one carry flag. MIPS has delay slots and things like that. If you want to make a portable decompiler that can be retargeted and to be used for another processor, then we better do not work directly with the processor instructions, but work with some our own language that will help us to implement the analysis only once, and then we can reuse it for other processors. Is it difficult to implement an intermediate representation or intermediate language? Well, not that difficult, in fact, because if you think about it, there are many other intermediate languages already present on the market. For example, LVM has its own intermediate language. There was Rail, Binary Nizia has own, and so on and so on. So we could use something existing. In fact, yes, that's right. We could use, and why do we use our own one? It's just because we started earlier than everyone else. I think that I started to write the decompiler maybe in 1999 or even 98, and at that time, even LLVM was not really existing. So we already had some kind of intermediate language, and it was already called Microcode. It was looking ugly at that time. You see how it looks. We have uppercase register names, double commas, and things like that. But it was simple, and it was already robust. And over time, it evolved, and the name Microcode does not mean anything. It's just kind of one processor instruction is split into multiple micro instructions. That's why it's a name. Of course, it is impossible to design something from scratch and to get everything right. Of course, our microcode had some shortcomings, some bad design decisions, and therefore we had to reverse them, change the microcode. And so it was an evolution, a very long evolution. And even today, we suffer from the bad design decisions that we made in the past. And well, we'll try to fix them, but some of them are very difficult to fix. Well, anyway, I think that I better continue with the instruction, in the description of microcode. What the design highlights, that's something that we always wanted to have with microcode. Of course, it should be universal. There shouldn't be any processor-specific stuff. Micro instructions should be very simple. One instruction does only one thing without any side effects. Very small number of instructions. We started with 45 in 99, and now we have 72, just because we added new functionality, like, for example, floating point arithmetics. It was not existing before, and we added it. The instruction operands should be very simple, like we have registers, numbers, and memory operands, and nothing else. Well, that was the beginning, and later we had to add many other things. And another limitation is that we will consider only compiler-generated code, because as soon as you talk about manually crafted assembler code, all bets are off, because it's possible to do anything you want with the assembler code, and you can even make something like, you say, add a constant to a register, and in reality this instruction gets executed as subtraction. It is possible to do it this way. So we don't go there, we don't consider manually crafted code. So globally it must be simple. And second thing is that we have to give up immediately on some fronts and say, we don't, for example, care about the instruction timing. Anyway, it's impossible to do with it, because we will optimize things, we will remove some instructions, and the timings will be completely wrong. The instruction order, we take this liberty of shuffling the instructions, provided that the outcome is the same. it is a problem with the exception, because if we reshuffled, we reordered two instructions, and an exception happens on the first instruction that was initially first, then the effects of the second instruction will not be carried out. So exceptions are a big problem for any decompiler, because they just disable all optimizations, and the decompiler without optimizations is not good enough. And, well, I saw order of memory accesses that I told, and handcrafted code, no way we can do it. I will, maybe I will just show you how the microcode looks like. Let's take this example. We have two moves, a subtraction and a conditional jump. This code is translated into something like this. So the first move is translated into, we form the address, then we use the LDX instruction, micro instruction, to load something from the memory, and we put it to the right register. So in total, it got expanded into 5 micro instructions. So we had only 5 processor instructions, and you see how many micro instructions we have. And it's a bit difficult to read because it's very verbose. Immediately after that, the decompiler will try to optimize things and will remove all redundant instructions, and then we will end up with much shorter instruction sequence. You see that we have only 9 instructions now. Well, it's still a bit verbose, because we, for example, set the 0 flag, a parity flag, and maybe they are not used in other parts of the program, but right now we cannot tell about it, because the first pass just does local basic block level optimization. Then we will perform other microcode transformations. For example, we will propagate the information globally between basic blocks, and then eliminate all redundant or useless instructions. And you see that we end up with 3 instructions, which is quite short. It's quite short code now. I like it better than the initial processor instructions that we started with. And finally, we will even propagate one instruction into another. For example, you see that we have just one instruction now. It says, if jump 0, then we have a very, very big condition, then jump to the block number 7. It happened so because the LDX and sub instructions got propagated inside the jump 0 instruction. And the final code is ready to be translated to C3, or if you present things in a C-like pseudocode, then we will end up with very nice one line saying that if the argv blah 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 equals to A, then we do something. So that's how it works. You see, that's quite simple, but as you know, the devil is in details. The thing is that how do we go from the verbose initial RISC-like microcode to this one-line code that we had at the end? Well, I cannot explain everything right now, but I will tell you a bit more about the steps. Let me describe the microcode a bit in more detail. You see that we started very simple, with very simple instructions, and every instruction had 3 operands. We call them left, right, and the destination. I don't know why we use these names, that's how it is. We transform the microcode, and nested sub-instructions appear, and so on, and so on, and so on. By the way, all this code is written in plain C++. We don't use any kind of machine description languages or whatever like LLVM does. Maybe it's their approach is of course superior, but this microcode thing and the whole decompiler is kind of research, and we are trying different things, and it's easy to try using C++, hard, well, everything coded in C++ rather than one more level of complexity of having machine description languages or whatever. Okay, let me quickly browse all these micro instructions that we can have in the microcode. First of all, we should be able to move values around. So we have two instructions for that. Move just means left to the destination, and LDC stands load for load constant. Very simple two instructions. Then, since in real-world programs, values are sometimes truncated, sometimes expanded, zero extended, or sign extended, then we have when we need micro instructions to handle that as well, like extend sign, unsigned takes low part or the high part of the operand. They make our lives much more difficult, but we need them because otherwise we will not be able to represent real-world programs. Naturally, we have load and store from and to memory. In theory, it can work with segmented processors, segmented memory, I'm sorry, because we work with selector and offset pairs initially, but in reality, in practice, we don't use these pairs yet. We just use data segment or code segment because all modern compilers use flat memory model, and in theory, it is possible to handle segmented memories with this microcode. It is possible. Then we have a set of comparisons. So we compare left against right and store the result into a so-called bit register like a carry flag, zero flag. You see that these instructions mimic what normal standard traditional processors have. Very standard stuff. We have lots of arithmetic and bitwise operations. I don't see anything to say about them, just the standard set. Please note that we have signed and unsigned division and modulo operations. We need them. We have set a group of sets. So shifts, I'm sorry, so we can shift a value to the left, to the right, shift to the right logically or arithmetically. By the way, in the past we used to have rotations, rotate to the left, rotate to the right, but we understood that it's no use because it's impossible to do anything with the rotation. There is no corresponding operation for rotations in C or C++, and therefore we just decided to drop them. This group of instructions is kind of odd because we talk about generating a condition code for an operation. For example, the first one, CF add, means add left to the right, calculate the carry bit of the operation and store it into the destination. Such an instruction does not exist in traditional processors, but this is a side effect of the add instruction. So when you say add, the processor adds two things and stores it at the destination, but it also updates the carry flag. Since we want to split the operations and every micro instruction does only one thing, we have to split it into a separate micro instruction called CF add. Similarly, we have OF add and the same thing for the shifts. Normally, these instructions have a very short lifetime because sooner or later the decompiler will either use the result, the carry bit, in some let's say, in some other place and consume it, or otherwise it will delete it because it is not used by the program. Naturally, we also have flow control instructions. We have indirect jumps, and we have simple go-tos, which means that go from one basic block to another basic block. The calls, we have two different calls, direct and indirect calls, and finally the return instruction. The call instructions are quite complex things because when we talk about calls, we have to talk about calling conventions, the arguments. Each argument has its own type, and if we talk about variadic functions like fprintf, then the number of operands can vary from one call to another. All this information can be represented in the microcode and can be played with. So that the call instructions are one of the most complex instructions in the microcode, but it's understandably why it is so. In addition to unconditional jumps, we have also conditional jumps when we compare two things and we jump to the destination if the condition holds. And we have one more quite odd micro instruction called jump table, JTBL. It is used to represent the switch idioms when we have cases and jump targets. Such an instruction does not exist in traditional processors because it is usually emulated, let's say, by a sequence of instructions, and we try to recognize the sequence and convert it into a jump table instruction. Finally, we have floating point operations. Nothing special here, addition, subtraction, and other stuff, plus conversions from the floating point to integer and back. So we can convert floating point to unsigned or signed integer, or the opposite direction is from integer to an unsigned, to floating point. It is also possible. Surprisingly, that a very short group, you see that this group is has only 10 instructions. It is enough to represent all modern programs with floating point operations. Something more complex like a square root or logarithm can be represented by a helper function. In the decompiler, we have so-called helper functions, and when we encounter something that we cannot represent in microcode in a nice way, we can end up calling a helper function called, for example, square root. And the decompiler does not really know what the square root does, but who cares? It's just a function name. So that's good enough for us. And I have to mention also about the last group. It is the external miscellaneous instructions. No operation, undefined. The most interesting instruction in this group is external instruction, EXT. Naturally, our microcode cannot represent all possible instructions of all processors. There always will be something that cannot fit in that cannot be represented in microcode. Take, for example, vector operations, the latest AVX instructions from Intel, and so on and so on, or privileged instructions that are used only inside operating system. These instructions cannot be represented in microcode, and for them, we just generate something called external instruction. External instruction is something that the decompiler does not know anything about it. It just knows that it has two operands, left and right, and the destination. We need these operands to carry out the data flow analysis, but otherwise it's kind of black box for us. We don't know anything about it. And finally, we have the undefined instruction. I did not tell about it. It is about saying, like for example, that some particular register is not is spoiled by at that moment. That's what we use. That's it. You see that we don't have that many instructions, only 72. Maybe we could extend the microcode to be more powerful, but right now we don't feel the need. It looks good, and it is really good. I mean that it can represent real-world programs. If you have used our decompiler, you know that it does a really good job for compiler-generated code. Now about the operands. The operands, well, we started as anyone else in a very simple things. So we have numbers and registers and nothing else. And if you take most theoretic papers about data flow analysis, they talk about integers and registers most of the time. But in reality, things are not that simple, and we had to add many other operand types. Since there are stack variables that are located on the stack frame, we added stack variables. Then global variables come as a logical continuation. Then we added many other things. Let me tell you about the most interesting thing. Well, let's review them very quickly again. Register operands. We do not use the registers, the processor registers directly. Each processor has its own registers. We don't want to handle them. We want to have something unified view of processor registers. Therefore, we map processor registers to micro registers. And each micro register has a number. Its ID, like 8, for example, means micro register. The micro register 8 is usually mapped to AL. 9 is mapped to AH, and so on and so on. So this way, we map 1 byte into 1 micro register. And this mapping helps us to get not to have this headache of partial registers, combined registers. Everything is kind of handled for us magically, because we have a very uniform view of 1 microregister is 1 byte. Very simple thing. And we allocate these microregisters during the microcode generation as needed. We need more registers, we can allocate more registers. In the future, I had this bright idea, bright and quotes, that why not map the stack frame into these microregisters. Since we have plenty of them, we are not limited by anything. Then we should we could map everything to this to the micro registers, and therefore we just use the same logic. We don't need to implement a special logic for stack operands. It turned out to be a bad idea. Initially it worked well, but then we had to do something. We will have to solve this problem one way or another. It's kind of laziness pays off, but in this particular case, it's in a negative sense. When we map, when I say that we map stack to microregisters, in fact we cannot map everything to microregisters, because some of the stack is referenced indirectly. For example, we can take an address of a stack variable and then pass it to a function. And the function maybe will modify something in our stack frame because we passed a pointer to it. Therefore, we cannot say that we cannot perform data flow analysis for that part of the stack frame because it is so-called aliasable. It can kind of change its value magically for us because some called function changes it. Therefore, the red part of the slide cannot be participate in data flow analysis. Therefore, well, not either, but the decompiler has to keep track what stack addresses we took, and therefore what part of the stack is aliasable or not aliasable. The more we improved the decompiler, the more problems we encountered. For example, the 64-bit values in 32-bit programs, or we can say 128 values in the 64-bit programs. Since such a big value does not fit into one register, compilers use two registers for them. It's a standard pair like EDX or EAX. Yes, it works well. So initially we just said, okay, it's a pair of instructions, registers. What about mapping them to micro registers in a way so they adjacent to each other, so they get lumped together into one big micro register. It worked well for the cases when we used EDX and EAX. But compilers got better over time. If 10 or 20 years ago, compilers would never do something bad like this, but now we can even see a pair of stack location and registers. Like, for example, SP plus 4 and TSI can together hold a big value, a 64-bit value. Therefore, we have to represent such values in the microcode, and we ended up with a new operand type. It's called operand pair. It has two pair parts, low and high part, and they can be located anywhere. Global memory stack, registers, and it's really used by modern compilers. And a decompiler that does not support an operand pair will not be able to generate nice decompiler, nice output. Unfortunately, the nightmare does not stop here, it just begins, because modern compilers can do even nastier things, and they can hold an operand not only in two registers, but even three more, including the stack frame, not continuous stack frame allocations, and everything like that. This is also possible. So a value is scattered over the different locations. It is not in one precise location, but it is also on the stack, for example. Well, we had no choice, and so we ended up one more operand type. It's called scattered operands, and they can represent all the above. It is very difficult to handle scatter operands, but we are doing our best. And while the support is not complete yet, we can handle many most common cases. Take, for example, this example. We have a function that returns a structure that consists of two parts, a quotient and a remainder. It is a division function that returns both of them at the same time. So you see that we take, and the entire structure is returned into RAX register. And then in the assembler, if you look at it, you see that we will take the low part and take the high part of the RAX register and do something with them. Since we support scattered operands, the compiler can represent it like this. So you see that we take the quotient, we add it to the location pointed by A1, and then we take the remainder as well. Similar situations exist for all 64-bit processors. This scattered operand thing is very not popular, let's say. It's a standard thing. It's defined by ABI. We have no choice. It's difficult to support, but we have to support them. Otherwise, it is impossible to generate nice code. So this was about the operands. I did not tell you everything about the operands because there are many other things, many details. It becomes too boring if I stop on all these details. Let me now talk about the transformations. What kind of transformations we do? Well, I will not again explain everything, but just some stuff. The initially what we do is something called pre-optimization. It's a very simple constant propagation algorithm. It propagates constants and registers as well. It's very fast, blazingly fast. But it gets rid of most temporary registers and divides the microcode size by 2. So we have a much shorter microcode. And by the way, this microcode looks very nice. It can be used for data flow analysis tasks. The next step is to work with a more complex propagation algorithm. It works on the basic block level, so we take one basic block and we see that if register is defined in one place and used in another place, we will just try to propagate the register value to the use location. It is much slower because we can try to handle many special cases, but it produces much better results. It can handle partial registers. For example, we take EIX and copy only part of it into another instruction, and so on. After locally optimizing the microcode, we optimize it globally by building a control flow graph and performing data flow analysis. So we find where each operand is used or defined. And this use or definition information is used for many tasks that the decompiler does. To delete the dead code, to propagate operands across basic block boundaries, and to generate assertions for future optimizations. Let me show you, I have a slide for that. If you have a conditional jump, we jump if not 0, if EIX is not 0, then we jump to the block number 5. Otherwise, we jump to the block number, we don't jump, we just continue to the next block. If you follow the false edge, the red edge on this slide, then we are sure that EIX is 0. But it's not explicitly expressed in the microcode. Therefore, we generate a so-called assertion. An assertion is a micro-instruction that says that EIX has this value at this point, and later this move instruction will be propagated and it will lead to more simplifications. That's one of the transformation rules that we use. In fact, there are tons of transformation rules that we use. Most of them are very simple. Like, for example, x minus y plus y is always equal to x. So therefore, we can simplify things and we can replace this complex expression by simply x. There are many transformational examples. I would say that there are hundreds and hundreds of simple transformation rules. They are simple and they are very they are sound in the sense that they never generate wrong code. We don't try to guess anything. Our transformations are solid and sound. In fact, the entire decompiler engine, the microcode, transformation rules, and everything, it is sound in the sense that all the transformation rules, they work. First we verify the conditions, and if the conditions are satisfied, then we do the transformation. For example, again, x minus y plus y. We check that the minus something and plus something, are they equal? They are equal. Do they have side effects? They don't have side effects. The two conditions are satisfied, therefore we can simplify things. And this works very well. The entire decompiler engine is sound in the sense that the rules are good, but sometimes the decompiler has to guess something. For example, we call a function. The function can be standard call. Maybe it returns result in EAX, maybe something else. And there, the decompiler has to guess. It has to say, okay, this function, maybe it accepts 5 arguments and returns 1 argument. Maybe not. If the guess is wrong, the output will be wrong. But otherwise, it is correct. But these kind of things, you can tell the decompiler saying that I know that the function, the function prototype for this call is this or that. You can say so. You can say so. Yes. One more thing is that all our rules, they don't depend on any compiler. So when when someone asks us what compilers do you support, we can say, well, in a sense, all, because the core of the decompiler does not depend on any specific compiler patterns or rules or whatever. Another example of a more complex rule. Some rules are very complex. For example, here we have a sequence of 2 subtractions we subtract low parts of operands, and then we subtract the high parts of the operands. Then these two instructions can be collapsed into one nice subtraction that subtracts 8-byte values. And there are tons of rules like that. Each rule is simple, and they work. Imagine that an ant hill. The ants running in all directions, doing this and that, but we have something similar. And all these ants working together, finally they produce a nice result. When these ants or rules try to match something, for example, we had these two subtraction instructions. We don't naively match them one subtraction instruction and immediately after that another subtraction instruction. No, instead of that we use data dependency rules. For example, on this slide we have the multiplication rule, which says that if you multiply the low parts and then we take the low part of the higher, then we multiply the higher parts and we store it into the high part of the result, then we can combine it into a nice multiplication like this. But between the multiplication and the low instructions, there can be other instructions. We don't really impose anything here. We just check. We just look at the data dependencies. For example, we will look for the instruction that accesses the X operand, and we will eventually find the low instruction. If you don't find it, then too bad, then the rule will not be applied. More about the dependency rules and data flow analysis I will tell you a bit later. Let me continue with other things right now. Some rules work across multiple blocks. Imagine that we have quite complex data control flow. There are three comparisons. First, we compare the high parts twice, J less or J greater, and then neither of them work, which means that the high parts are equal. Therefore, we compare the low parts, J below, jump below. All this construct can be replaced with one JL, but here we use a 64-bit values. Another example of interblock rule. We have three blocks, jump conditional if the value is less than 0. If it's not less, then we jump to shift instruction, otherwise we add something to the value, and this rule gets transformed into a sign division. Why do we have such a rule? Because many compilers optimize a division by a shift. Shift is much faster than division. Therefore, they represent things this way. But for us human beings, it's easy to have the sign division rather than comparison, then addition, and then shift. So this makes things much simpler for us. Okay, now we have so many rules and so many transformations. What can you do with this microcode, and what can you, how you can play with it? In fact, it is possible using the SDK to attach, let's say, to hook to the optimization engine and to add your own optimization rules. You can say, for example, that if some conditions are satisfied, then you can simplify the microcode this or that way. In fact, such hooks are already used internally by the decompiler itself. For example, the ARM decompiler has the following rule. If we have an indirect jump using the initial value of the LR register, usually it means bxlr, it is the same thing that return. The ARM programs have the return instruction disguised. They use bxlr instead of ret. And this is something specific to ARM, and therefore the ARM decompiler has a hook that recognizes this indirect jump LR and converts it into a simple return instruction. There is one question here. How do we prove that the LR at the instruction BX is exactly equal to the initial value of LR? For that, we have to perform the data analysis. The decompiler engine and the microcode use data flow analysis very, very extensively. We have, maybe you already noticed that all instructions that we have here, for example, move, for all instructions we also show the U equal and D equal things. They are shown in red on the slide. They show us what is used by the instruction and what is defined by the instruction. For example, the move instruction, the first one, defines EBX and uses the arg+4 stack variable. These lists are calculated when necessary, and the decompiler relies on them even more than on the instructions itself. We don't go backwards, for example, searching for the move instruction. No, usually we just say, find me an instruction that will define EBX, for example, and we can go backwards or forward, find the interesting instruction. Similar use and definition lists are maintained for each block as well. Here we keep them pre-calculated instead of recalculating on demand, because basic blocks can be very big and therefore it can be very expensive. By the way, one of the things that we try to do with the microcode is to stay very efficient. I'm proud to say that we really achieved our goal, because if you take our decompiler, it can decompile in stuff. Most stuff can be decompiled within instantaneously, within seconds, whatever, very, very fast. There are other decompilers that you can play with, most of them are free decompilers, and the speed is 10 or even more times slower. Just because I would say explain this by our attention to the efficiency. Almost everything in the decompiler is written in a very efficient way. We use C++ and we don't, and every time we see something can be optimized, we sit down and optimize it. And we try to keep our code base in a very clean, so it's clean, nice, and we are not really ashamed to show published part of our code to you, so you can use it for your own purposes. By the way, 2 days ago we published quite big part of the decompiler that verifies the microcode consistency. You can see our coding style, and you can understand what microcode is considered to be correct and what is not considered to be correct. For the use and let's return to the use and def lists. For them, we keep must access and may access lists. If you are familiar with the data flow analysis, this will tell you something. Otherwise, I'm sorry, I will not be able to explain things in detail because we don't have enough time. I think that I will continue with the use def lists and explain what are the usefulness of the use def lists for the decompiler, and not only for the decompiler, but also for you, if you decide to use our microcode for some data flow analysis tasks, let's say, the tasks that rely on the data analysis. This use def chains or lists, they can easily answer questions like, is the defined value used anywhere? If it is used, where exactly? In one location, many locations? Give me all locations. Can we move the definition to the use place? And things like that. There are many questions that can be easily answered, and this can well, simplify your life if you decide to use this microcode. Oh, there are many questions that can be answered using this. I will continue with the other things. Let me show you a couple of slides with another example. Imagine that we have 3 blocks here. There can be more, but on my slide I have only 3. We move a constant 5 into a register. Then the second block does something but does not touch ESI, does not modify. And then we call a function using ESI. We perform the data flow analysis, and we end up with a use and def list like this. You see that for the first block, we have the definition of ESI, and it says that this definition is used in the block number 3. Therefore, we go to the block number 3, and there we see that the value comes only from one location, from the block number 1. Therefore, since one location defines, one location uses, we can take the value and copy it to the call site, and we end up with call 5. Call function with argument 5. It's a very simple thing, but this is the idea of global value propagation, and it works very well. Well, there are many other things I could tell you about microcode, but I think that I will stop here. Otherwise, maybe it becomes boring. And second, we are running out of time. So, just a few common words about the microcode. The microcode object is a very complex object with many rules. For example, if we say that the add instruction, we have left operand plus right operand equals to the destination. So we should have left and right operands, and they should be registers, whatever. So it must be consistent. If you end up with a microcode that is inconsistent, then everything will be wrong. Therefore, we verify the microcode consistency after every transformation. And if you do it, if you write a plugin for the decompiler, you should do the same. And because of that, we have very few microcode-related bug reports. But if you want, you can send us a bug report about it if you stumble on any bug report. We have a very extensive test suite that some of our tests run, let's say, literally for weeks. I think that we have a cluster of servers that continuously decompiles things and runs and compares and verifies that the results are good. Therefore, our decompiler is very robust, including the microcode. Anyway, if you find the bug, send us a message. We try to fix things very fast, one day or even faster most of the time. If something blocking, of course, if you complain about something that it's not blocking, then it's not that important. It can wait. Everything that I explained here is available since 2 days already. We published it, and you can already start to implement things in C++. Python is not available yet because it takes some, it will require some more work from us. There are quite many sample plugins that come with a new API, and we will blog about it, and we will explain more things, what to do this and that. There are very interesting ideas what can be done with the microcode. Anyway, we will be happy to hear your technical feedback about it, and we always open on these kind of things, and don't hesitate to send us a message about it. I think that's all. I try to keep it short. Thank you for your attention.
there to no reversers in the room or...
No problems. If you have any questions, you feel free to ask me later.
Hello.
Thank you.
Hello. First of all, thank you for this absolutely wonderful presentation of an incredible quality. And my question is, to what extent is this technology effective with medium or large programs? To what extent can it transform a program, a medium or large program, say like Microsoft Excel, to a machine independent representation? Are we far from a day where we can convert a commercial program to a machine independent representation and port it to a different processor without the help of the vendor? Thank you very much.
Okay, thank you for the question. In fact, we do decompile Excel and other big programs without any problems. It will take longer, of course. It will take maybe a few hours to decompile such a big thing. And in the past, we had some problems with, let's say, Chrome. Chrome is one of the biggest applications we have in the world now. But even that, we had problems not because of the decompiler, but because the whole ecosystem, the decompiler was a 32-bit program, and we were running out of memory. Because we could not keep everything in the memory. But now we use 64-bit memory, and Chrome can be decompiled as any other thing. But if you talk about converting it into another architecture, then there can be some other obstacles because, as I mentioned, the decompiler has to guess some information because the information is missing from the binary. The function prototypes is one of the biggest things that we have to guess. Let's say 98% of time we guess correctly, but this 2% that will spoil everything, and you will have to find all these wrongly guessed prototypes and fix them. There can be other problems like for example, we misdetect the function boundaries, or we misdetect the stack pointer, we track it incorrectly. These are generally unsolvable problems. It's not only a shortcoming of either or a decompiler, it is a generically unsolvable problem. We can only approximate, and with the help of the user can always correct us, saying that we know that here the function should look like this, it accepts this number of arguments and everything. If you get everything correct, there's no obstacle from the microcode. The microcode itself can handle big real-world programs, and we do it every day as part of our tests. Did I answer your question? Okay. Thank you very much. Thank you.
More questions? There we have one. Here.
Okay.
Stand up, please. Stand up, please.
No problems.
Just a second.
Hi, congrats for the talk. Sometimes when you're coding, you need to go down for some very low-level procedures. For example, when you're working with cryptography, you need to do sometimes inline assembly instructions. But it seems you sacrifice some instructions. For example, rotating or shifts or post-decrement, post-increment instructions. Don't you think that affect the flexibility when you're working and you need to go down, because sometimes a cycle of processing, it's really critical?
Yes, it's right that the microcode cannot represent, for example, as post-increment or other things, but it doesn't mean that we lost the information. We just represent things differently in the microcode. Instead of post-increment, we just say add 1 to a register. And we keep it this way all the time, along until we reach the end of the decompilation and we generate the output. At the output generation time, we have kind of some magic that takes that looks for the pattern. A equals A plus 1. Okay, it's the same thing as a post increment. And at that moment, we do post increment. So for the user, he sees a post increment as if it is supported. Internally, it's not supported, but the end result for the user is good. So we don't lose any information here, even if you talk about square roots, whatever, everything that is not supported in the microcode directly, we still carry the information along in the microcode, and we will represent it in a nice way. For example, as an inline assembly, take rotations, for example. We don't know what to do with them, and at the end, they will be displayed as a rotation. As an assembler instruction, because we cannot do anything about them, yes, it's ugly, but we cannot do it better because in C, there is no way to display nicely rotation. That's why it is like so. So you don't lose any information here. No.
Cheers.
More questions? Okay.
Okay.
Thank you so much.
Gracias.